जी हेलो अस्सलाम वालेकुम।
वालेकुम अस्सलाम सर।
वालेकुम अस्सलाम।
Okay, in the last two sessions, Professor D'Souza discussed some things which we will discuss briefly again today. So in the very first class by Professor, he discussed the vector space. So vector space, a non-empty set with two operations, vector addition and scalar multiplication, satisfying certain properties. So for example, vector addition is commutative x plus y equal to y plus x. It is also associative x plus y plus z equal to x plus y plus z. So you can put bracket anywhere you would like. So you can add y and z first and then add x, or you can add x and y first and then z. The answer will be the same. So in vector space, there is a zero vector, right? So every vector added to the zero is equal to the vector. And for every vector x, there is another vector that is called minus of the vector. If you add both, answer is the zero vector. And then some properties with respect to the scalar multiplication. So alpha beta x equal to alpha beta x. So you can put bracket anywhere. So when it comes to a scalar multiplication, this bracket does not matter. And there is a scalar that is called 1. If you multiply that scalar with any vector, the answer is the vector itself. And then distributive laws, scalar times sum of the vector is equal to sum of their scalar multiplication. So alpha times x plus y equal to alpha x plus alpha y. Similarly, distributive property with respect to the sum of the scalar. So alpha plus beta time x equal to alpha x plus beta x. So alpha, beta, gamma scalars are coming from the field. So you can consider any field, but in this course, we will consider the field of real numbers or the field of complex number. So using the properties of scalar multiplication and vector addition, you can have these properties. So if you multiply any vector with the scalar 0, you will get a 0 vector. Or if you multiply any scalar with the 0 vector, you will get the 0 vector. And if you multiply -1 with any vector, you will get the minus of the vector. So then you can go through these spaces. Space Rn, we already have discussed this space. This is a Euclidean space. Every element is n tuple. So there are X is an element of Rn that consists of n tuples, xi1, xi2 up to xin. Y, eta1, eta2 up to eta n. So how do you, so this is a vector space with the algebraic operation defined as, so you can add two n tuples. So x plus y is equal to xi1 plus eta1 up to so on xin plus eta. And you can add the corresponding coordinates. So first tuple of x will be added to the first tuple of y and up to so on. Similarly, scalar multiplication. So you can multiply scalar alpha with x by multiplying alpha with every tuple xi1 up to xin. So similarly, space Cn, it is a space of n tuples of complex numbers. So ordered n tuples of complex number. So every tuple is a complex number. For example, x equal to xi1 up to xin. Each xi is a complex number. Similarly, y is a ordered n tuple of complex numbers eta1 up to eta n. So algebraic operations defined very similar to the algebraic operations we defined for Rn, x plus y, and alpha x. So then space of continuous functions defined on the interval AB. So you can add two functions. So x plus y, sum of two functions, is a function. And what is the definition of the function? Sum of the function x plus y. It is defined at t by this formula. X plus y at t will be equal to xt plus yt. Alpha x is defined at t as alpha multiplied with x at t. So you can call it pointwise addition and pointwise scalar multiplication. So with these operations, vector addition, function addition, and scalar multiplication, CAB, space of continuous functions defined on the interval AB, it is a vector space. So you can verify on your own all the properties of vector space are being satisfied. Similarly, just as a small exercise, you can show Rn and Cn are vector spaces. And then we have L2. You are familiar with L2 sequence spaces. So you can add two sequences by adding the corresponding terms of the sequence. So if you have a sequence xi1, xi2 up to so on, eta1, eta2 up to so on. So sum will be xi1 plus eta1 up to so on. Similarly, scalar multiplication. So L2 is also a vector space with these two operations. So other vector spaces you can consider L infinity, space of bounded sequences, LP for p greater equal to 1 less than infinite. So these are vector spaces. So maybe we need these definitions. A subspace of a vector space is a non-empty set which itself is a vector space, satisfies all the properties of being vector space. Subspace of a vector space satisfies all the properties of being vector space under the same addition and scalar multiplication we have for X. And then there is a definition of linear combination. So we have a vector space X and vectors X1 up to Xm. So linear combination is alpha 1 x1 plus alpha 2 x2 up to alpha m xm, where alpha 1 up to alpha m are scalars. So that is called linear combination. So if we have a subset M of a vector space X, so if you collect a set of, if you collect all the linear combinations of vectors in the subset M, the set of all the linear combinations is called span of M. Span of M. So span of M is a subspace of X. You can prove that actually. You can consider proving it as a small exercise. It shouldn't be difficult. You must have studied linear algebra or calculus somewhere. So span M, where M is a subset of X, is a subspace of X. So subspace, the definition of subspace, it is a subset of a vector space. It is vector space under the same addition and scalar multiplication. Or alternatively, you can check if you consider any two elements from the subset y, y1, y2, and if you consider the linear combination alpha y1 plus beta y2, so this belong to y for all y1, y2, and for all scalars alpha, beta. So if this property is being satisfied, then Y is a subspace. No need to check all the axioms of a vector space, just this one property. So similarly, you can check span of a subset of a vector space is a vector space. So then linear independence of a set of vectors, for example, we have a set of vectors x1 up to xr in the subset M. So there are vectors x1 up to xr. So M consists of vectors x1 up to xr. And it is a subset of vector space X. So this subset M, or the vectors x1 up to xr, are linearly independent if this equation alpha 1 x1 plus alpha 2 x2 plus up to so on equal to 0 has only one solution for alpha 1, alpha 2, alpha r, that is 0. If alpha 1 x1 plus alpha 2 x2 plus up to so on alpha r x are equal to 0 implies alpha 1 equal to alpha 2 equal to up to alpha r equal to 0. So then we say that x1, x2, xr are linearly independent, or set M is linearly independent. So of course, if you will put alpha 1, alpha 2, alpha r equal to 0, the equation is being satisfied. So if these are the only values, alpha 1 equal to 0, alpha 2 equal to 0, alpha r equal to 0, for which this equation is being satisfied, then we say that x1, x2, xr are linearly independent vectors, or the subset M consists of these vector is a linearly independent subset. So a vector
सर आवाज नहीं आ रही.
आवाज नहीं आ रही. सर ऑफलाइन हो गए थे.
सर का आई थिंक इंटरनेट प्रॉब्लम है, सर लीव कर गए.
Okay, so in vector space, in vector space X, so we can define the linearly independence of any arbitrary subset. So that subset can have a infinite many vectors in it, or maybe uncountably infinite vectors in it. So we can define, so what does it mean by linearly independence of any arbitrary subset of a vector space? So we say that any arbitrary subset M of X is linearly independent if every non-empty finite subset of M is linearly independent. So M is said to be linearly dependent if M is not linearly independent. So it is linearly independent if every non-empty finite subset of M is linearly independent. It is not linearly independent if every non-empty finite subset of M is not linearly independent. That means there exists some finite subset which is not linearly independent. So then, well, these are the things we will need. So you need to revise. If you do not know these preliminary notions, you can revise from any book on linear algebra or from this one as well. So let me call so we have finite and infinite dimensional vector spaces. So a subset of a vector space is called basis if it is linearly independent and if it spans the whole space. So a vector space is finite dimensional if there are finite many vectors in the basis of a vector space. So, or in other word, another way is, so a vector space is finite dimensional if there is a positive integer n such that X contains a linearly independent set of n vectors, whereas any set of n plus one or more vectors is linearly dependent. So, so X is finite dimensional and dimension of X is n if there are n vectors which are linearly independent. But if you consider any set of n plus one or more vectors, any set that is linearly dependent, then we say that X is finite dimensional and dimension of X is equal to n. So for example, Rn is a finite dimensional, Cn is a finite dimensional, right? CAB is not finite dimensional space of continuous functions. LP is not finite dimensional. And then this result, every vector space has a basis. So you don't need to worry about. So every vector space has a basis. And then a result about subspace. So X is finite dimensional, then any proper subspace Y of X has dimension which is less than n. Proper subspace Y. That means there is at least one element in X which is not in Y. So strictly less will be the dimension of Y, strictly less than the dimension of X. So maybe you can consider some problems in this exercise 1, 2, 3, 4, 5. So as many as you can. Okay. So further, one more thing. The notes sent by Professor D'Souza, chapter number 1. So we will discuss some examples from those notes. So for example, examples of norm spaces. So consider the proof of, so prove that those spaces are vector spaces. So I will not do that in this lecture. So you can do at home. So these are the routine exercises you can prove easily that those are the vector spaces. So norm, you already know norm. Norm is a function that is defined on the vector space. So let X be a vector space So define norm on X such that so a function is a norm on X if it satisfies these properties for all X belong to X. And the other property is, so norm of X is equal to 0 if and only if the vector is equal to 0 vector. And alpha time X has norm which is equal to absolute value of alpha time norm of X. So for all alpha from field and X belong to X. And then we have the triangle inequality X plus Y, X norm plus Y norm for all X, Y in X. So these properties must be satisfied before we call the function norm. So every norm, so we can define a metric with the help of a norm. So normally we call it norm space. So we use this notation to represent norm space. X is a vector space and this function is a norm on X. So this ordered pair is called norm space. So define D so if we have X is a norm space, so we can define dxy is equal to x minus y for all x, y belong to X. So if we, every norm space is a metric space and you can define metric as this formula. So not every metric is in, so metric, you can call it metric induced by the norm. So you can, not every metric is induced by norm. So every norm induces a metric, but not every metric is induced by some norm. So for example, let me show you. Hello?
Yes, sir.
Yes, sir.
So can you give me an example of a metric space which is not induced by norm?
Sir, discrete metric space.
Why do you think discrete metric space is not induced by norm?
सर क्योंकि नॉर्म स्पेस होने के लिए वेक्टर स्पेस की कंडीशन होती है एंड आई थिंक जो डिस्क्रीट मेट्रिक स्पेस होती है वो वेक्टर स्पेस नहीं होती इसलिए
जो डिस्क्रीट मेट्रिक होती है वो वेक्टर स्पेस नहीं होती। कौन, सॉरी से अगेन, हेलो हेलो,
यस सर।
जी अभी कोई बता रहा था, सॉरी क्या नाम था अभी जो बात करी?
सर वो बता रही थी कि एक डिस्क्रीट मेट्रिक स्पेस जो है वो इंड्यूस में इंड्यूस नहीं होती, इंड्यूस नॉर्म नहीं होती, क्योंकि वो वेक्टर स्पेस की कुछ प्रॉपर्टीज को फुलफिल नहीं।
So let X be a vector space. So you can consider X equal to R, no? And define dxy equal to 1, X not equal to Y, 0 if X equal to Y. So, but R is a vector space, right? So R is a vector space.
यस सर।
So metric space is not induced by norm space. So if you have defined metric on a non-empty set which is not a vector space, okay, fine. But if it is a vector space, so can it be induced by any norm? So X equal to R is a vector space. So can it, this discrete metric on R be induced by norm?
सर सफिशिएंट कंडीशन कह सकते हैं बट नेसेसरी कंडीशन नहीं कह सकते इसको आई थिंक बाकी आप क्लियर कर दें
Sufficient condition. What is sufficient condition? Can you explain? So let me show you something. Okay, so these are the examples you need to work out to show that these are norm spaces. So for example, I will come back to this point, discrete metric, whether it is induced by norm or not. So Euclidean space Rn. So every ordered n tuple, we can define a norm by considering the absolute value and then square of every tuple and then square root. So similarly, we can define norm on Cn. So these are norm spaces, so you can prove easily. So dxy can be defined x minus y norm. Right? Similarly, you can define norm on space LP. So x is a sequence. So x norm is equal to, x is a sequence which is equal to xij. So x is a sequence which is equal to xi1, xi2 up to so on. So you can define norm by this formula. So the metric induced by this norm is equal to this one. So this is a metric we consider in chapter number 1. So similarly, L infinity is a norm space. So So X is a sequence, xi1, xi2 up to so on. Norm you can define this way. Metric induced by the norm is this one. Similarly, you have Bell infinity, you can define norm by X is a sequence, bounded sequence. L infinity is the space of all bounded sequences. So norm of a bounded sequence is the supremum of absolute value of xi. So you can consider the absolute value of each term of the sequence and consider a supremum. Sup exists because it is a bounded sequence. Similarly, we have CAB, space of continuous functions. So norm is defined by this formula maximum of x t. T belong to J. J is the interval AB. Okay. So this lemma provides a criteria. So if a metric D is induced by a norm on a norm space X, then this metric satisfies these two properties. So distance between X plus A and Y plus A. So A is any, so X, Y, and A are any vectors in X, and the alpha is any scalar. So if you translate X and Y using the vector A, the distance remains invariant. So distance between X plus A and Y plus A is same as distance between XY. The other property is distance between alpha time X and distance between alpha time Y is equal to alpha mod dxy. So if these two properties are being satisfied, so these two properties are satisfied by the metric induced by norm. So if a metric is induced by norm, then these two properties are being satisfied. In other words, if these two properties are not being satisfied, then the metric is not induced by norm. So somebody was saying that it is sufficient. So let me describe what does he mean. So we have this implication P implies Q. So P is sufficient for Q. Or Q is necessary for P. So this is the language we use. So here in the lemma, if a metric if metric D induced by a norm on a norm space X, then it satisfies x plus a, y plus a equal to dxy and d alpha time x, alpha time y equal to alpha absolute value time dxy. So for all x, y, a in x and scalar alpha, right? So remember, if metric D is induced by norm, so it is sufficient for these two properties. So these two properties are being satisfied. So these two properties are necessary for a metric D induced by norm. So P implies Q. So we have something in the form of P implies Q. So P implies Q has equivalent form, not Q implies not P. So for example, if these two properties are not being, both are not being satisfied, then we say that metric is not induced by norm. So अगर आपने check करना हो कोई metric, whether it is induced by a norm or not, so you can check these two properties, because if there is any metric which is induced by norm, that will satisfy these two properties. So if these two properties are not being satisfied, then the metric is not induced by norm. So for example, the metric, this metric sequence space S, remember the space S, so it is a vector space. S is a vector space. It is a sequence space. Sequences can be bounded or unbounded. We defined metric dxy by this formula. So it is not it does not satisfy those two properties. It does not. So how to show that this metric D does not satisfy those two properties? So you can assume two sequences. So it's I and eta I, and show that those two properties are not being satisfied. So especially the second one, so when you multiply with alpha, right? That property won't be satisfied. So you can consider with this
Sir?
metric, yes.
सर हर्मिटिक स्पेस वेक्टर स्पेस होती है?
Metric space is a non-empty set. So we have a structure on the non-empty set. So that structure tells us how to find the distance between two elements, right? So if on a non-empty set X, on a non-empty set X, we can have a distance structure, we can have a distance function, but that non-empty set might not be a vector space. So for vector space, you need other operation, vector addition and scalar multiplication. So there can be a metric space which is not a vector space. There is no vector addition or scalar multiplication, but there is a
तो
distance.
सर अगर कोई ऐसी मेट्रिक स्पेस हो जो इन दो प्रॉपर्टीज को सेटिस्फाई करे बट वो वेक्टर स्पेस ना हो, तब भी हम कहेंगे कि वो मेट्रिक इंड्यूस्ड बाय नॉर्म है.
So metric इंड्यूस्ड बाय नॉर्म के लिए आपके पास नॉर्म स्पेस होना जरूरी है, राइट? सो नॉर्म स्पेस के लिए you need a vector space. So you define norm on a vector space. Right? So here we are talking about there are metrics which are defined on the vector spaces. So you can define a metric on any non-empty set. It can be a vector space and it cannot be a vector space, whatever it is, vector space or not. So you can always define a distance. So it can be a metric space. So metric space defined on the vector space, metric defined on the vector space. So this metric is defined on the vector space. So it is not induced by any norm. So we will not talk about the metric induced by norm, which is not a vector space. So keep it aside, right? So we are talking about the metric which are defined on the vector space. Those metrics are not induced by norm if they do not satisfy these two properties.
Okay, sir, got it.
So metric is more general structure. I mean, I like the example given by Professor D'Souza in his lecture last time. So in metric space, you have a structure of a house, so nothing inside, so no bed, nothing. So in norm space, you have more property. You have the distance function as well, but you have much more inside. So this sequence space, for example, you can consider this sequence space xi 1, 0, 0 up to so on, and eta I is equal to maybe 2, 0, 0 up to so on. And then you can consider alpha equal to scalar 3, and then check whether this property holds true or not. D alpha x alpha y, x is this one, y is this one, whether it is equal to alpha mod dxy or not. So you can find many examples to show that this dxy by this formula, this sequence space is not metric induced by norm because it does not satisfy both properties. Maybe it satisfies one property, but it does not satisfy both properties. So now come to the discrete metric space, like if we have x equal to r and distance, r is a vector space. So dxy distance is defined by 0 if x equal to y, distance is equal to 1 if x is not equal to y. So is it a metric induced by norm or not? Somebody said no. So, but the reason is not the right that it is not vectors. It is a vector space. R is a vector space. So, but let's check, for example, the second property. For example, if alpha is equal to 3, and x is not equal to y, then distance between 3x, 3y is equal to 1. But alpha time dxy is equal to 3 time dxy, which is equal to 3. So both are not equal. So d 3x 3y is not equal to 3 mod dxy. So second property is not being satisfied. So it is a metric which is not induced by any norm. So there are some more problems you can find in the exercise. So this lemma is very simple, right? The proof you can see one line proof. So dx plus a, y plus a, because d is induced by a norm, so that is equal to x plus a minus y plus a. So this will be equal to x minus y norm, which is dxy. Second property, d alpha x alpha y is equal to norm of alpha x minus alpha y is equal to
using the property of norm alpha mod x minus y norm, which is equal to alpha mod dx. So you can check some problems in this. So consider this question number 6, for example. So consider set of all ordered pairs, xi1, xi2, eta1, eta2. So you can define norm 1 norm, 2 norm, infinite norm. So show that these are norms. So x, 1 norm, 2 norm, infinite norm satisfies the properties of being norm. 1 to 4 properties we discussed for a function to be norm. So you can check this. Similarly, you can extend it to the vector space of ordered n tuples of numbers. So 1 norm, p norm, infinite norm. So if you put p equal to 2, you will get 2 norm. These are the so our space vector space of ordered n tuples with these norm is norm space with each 1 norm, p norm, and infinite norm. So you can, that is the definition of a unit sphere in a vector space. So unit sphere in a vector space is a set of those vectors whose norm is equal to 1. So you can consider the set of ordered pairs, and you can consider the unit sphere with respect to 1 norm, 2 norm, 3 norm, 4 norm, infinite norm. So you can plot the unit sphere in R square in plane. It's a very simple case. So you will see that you will get different shapes of the unit sphere. You get square, you get circle, you get rectangle. So geometry depends on the norm of the unit sphere in R square. So then read this convex set in a vector space, right? And we'll discuss some more exercises in the next session. Hopefully in this week I will conduct one more session. Maybe along with Professor D'Souza, problem solving session. I will let you know. So question number 14 was the question we were talking about before. So metric induced by norm. So d tilde is a metric which is, d is a metric and d tilde is another metric which is defined with the help of the metric d. Show that d cannot be obtained from a norm, d tilde. So you can check, you can consider vector space X, you can consider X equal to R, you can consider some elements X, Y, you can consider alpha, you can consider those two properties for a particular value of alpha and X, Y. You will see that those properties are not being satisfied. So which are being satisfied for a metric induced by n norm. Okay, so few more notions in this section 2. So so one more fact, the norm is continuous. The norm is a continuous function defined on a vector space. And you can prove that norm is continuous using triangle inequality in 2. So triangle inequality y norm minus x norm, absolute value of y norm minus x norm is less or equal to y minus x norm. So using this triangle inequality, we can easily prove that the norm is continuous function. G, can you prove? So
सर ये प्रूफ करते हैं सर.
So
सर
yes. So f of x equal to x norm, right? So x belong to, for all x belong to x, where vector space and norm on x. So if you define this function fx by this norm function, this function is continuous function. So you can pick x naught belong to x. So we can show that f is continuous at x naught. So f is continuous at x naught if for every epsilon there is delta positive number such that x minus x naught implies f of x minus f of x naught less than epsilon. So that is the definition of continuity. So you can start for any given epsilon you can choose delta equal to epsilon, right? Such that we have f of x minus f of x naught absolute value that is equal to x naught minus x naught norm, and this is less or equal to x minus x norm by the triangle inequality, and this is less than delta, and delta is equal to epsilon. So that means for any epsilon there exists delta positive such that this property is being hold true. So you can write in the next line, right? So if x minus x naught norm less than delta, then from this one f of x minus f of x naught norm less than delta, which is equal to epsilon. So this implies that f is continuous at x naught. So x naught is arbitrary fixed vector in x. So norm is a continuous function on x. So just like complete metric space, we have complete norm space, which is called the Banach space. So complete norm space in which every Cauchy sequence is convergent. So what is a Cauchy sequence in a norm space? A sequence xn in a norm space x is Cauchy if for every epsilon there is natural number n such that xn minus xn norm less than epsilon for all mn greater than the natural number. So the convergence, if limit norm xn minus x is equal to 0, then we say that the sequence xn in the norm space converges to x. So then a subspace y of a Banach space x is complete if and only if the set y is closed in x. So this is very similar to the result we did for the metric space. So for a subspace in metric space, so if we have a complete metric space, then the subspace is complete, itself complete if and only it is closed in the metric space. So that is the analogous result of that result. So you can prove this easily on the very similar lines. So you have a Banach space. That means you have a complete norm, complete metric space, the metric induced by the norm. So try to prove it, try to write the proof, just following the proof of the analogous result in the section metric space. So then we have infinite series. So one of the most important thing about Banach spaces, theory of Banach spaces, is that you can do calculus in Banach spaces. In metric space, there is not much room to do many things, but in Banach spaces you can do many things which you have been doing in calculus. Like in calculus, we have the concept of infinite series. So in vector space, we can define a series. We can add two vectors. We can add more than two vectors. So we can define infinite series actually. So if xk is a sequence in a norm space, we can associate a partial sum. So Sn equal to x1 plus x2 plus xn. Partial sum, if you add one term of the sequence, that is S1. If you add first two terms, that is S2. Sum of first 10 term is Sn. It is a sequence of partial sum. So if this sequence of partial sum, so we know what does it mean by convergence of a sequence in norm space. Sn is a sequence. So if it converges to some vector in norm space, Sn converges to S. So then we say that the infinite series x1 plus x2 up to so on converges to that vector S. Sn is a sequence of partial sum that converges to S. That if Sn sequence of partial sum converges, then we say that infinite series is convergent and the sum is equal to the vector S, which is the limit of the sequence of partial sum. So then last time, I remember Professor D'Souza discussed with you the absolute convergence. So if the series of infinite series of the infinite series that is constructed by adding the norm of the terms of the sequence, x1 norm plus x2 norm plus x3 norm up to so on. So if this sequence converge, series converge, so series of norm, then we say that series 2 converges absolutely. So we have this series xi I from 1 to infinite. So converges absolutely if summation xi norm I from 1 to infinite converges. So absolute convergence implies convergence. So in calculus, where we consider a sequence and series of real numbers, complex numbers, so we will prove that series converges absolutely. So we'll say that it is convergent. The series is convergent if it converges absolutely. But here we, in that case, R is complete norm space, right? So in vector spaces, norm spaces, we will say that absolute convergence implies convergence if and only if the space is complete. So X is Banach space. So if X is Banach space, then absolute convergence implies convergence. So you have the result what you have in calculus, so you have in Banach spaces, the same result. So absolute convergence implies convergence. Using the concept of series, so we can define Schroeder basis for X. So E1, E2, En is a sequence in norm space. So if for every x, there exists a scalar such that x minus alpha 1, e1 plus alpha n, and this converges to 0 as n approaches to infinity, then we say that the set e1, e2 up to so on is a Schroeder basis for x. If the limit exists in 3 for every x in the norm space. So in that case, we can represent x as a linear combination of the basis vector, Schroeder basis vectors e1, e2 up to n. So these bases are called Schroeder bases. So you can represent a vector in the norm space as a linear combination of the basis vector, Schroeder basis vector. So LP has Schroeder basis, namely En. So E1 is the one at the first place, E2 is the one at the second place, up to so on, rest 0. So E3, 1 at the third place, rest component are 0. So E1, E2, E3 up to so on. So these form the Schroeder basis for LP. So we'll study, separable metric space. So if there is a countable dense subset, then the space is separable. So if X has a Schroeder basis, then X is separable. So the converse, so one of the important question in mathematics is to study the converse of the statement. So if X has a Schroeder basis, then X is separable. So what about if X is separable? So what about, so does every separable Banach space have a Schroeder basis? So the answer is no. So maybe we'll come back to this separability later in some stages. We'll discuss this. So in the section of metric spaces, we discussed the completion. So similarly, so like in that section, we discussed every metric space has a completion. Means that for every metric space, there is another metric space. For every metric space X, there is another metric space X tilde, such that X tilde has a dense subspace which is isometric to the metric space X. And X tilde is complete. So up to isometry, every metric space has a completion. Similarly, every norm space has a completion. So isometry in metric space that preserves the distance. So this proof is an so you can use the theorem 1.6.2, the previous section, to show that Banach space has a completion. But there is something more that like norm space has a structure of a vector space, vector addition and scalar multiplication. So you can transport you can define a vector addition and scalar multiplication on the completion as well. So vector addition and scalar multiplication is compatible with this completion theorem. So you can just read it. So let me discuss something from
सर ये बहुत नहीं आज के लिए सर।
आज का लेक्चर तो अभी रिवीजन कर रहे हैं हम, तो चीजें पढ़ी नहीं अभी।
सर एक तो नेट डिस्टरबेंस की वजह से ना काफी सारे पॉइंट अनक्लियर हैं बड़े, तो
नेट को क्या
इसलिए
हो
मैं
गया? What happened to your internet?
सर आवाज बार बार ड्रॉप हो रही है।
Okay. So okay, you can have a break for 5 minutes. So we'll discuss after
सर अभी
5
ब्रेक
minutes.
ना करें फिर नमाज का टाइम हो जाएगा सर।
कितने बजे होता है नमाज का टाइम?
सर 5:15।
सर हमारे पास 5 बजे है।
सर आपने कहा था कि नेक्स्ट लेक्चर में हम कोर्स कोर्स डिफाइन कर लेंगे, मिड के लिए, मिड टर्म एग्जाम्स के लिए जो होगा कोर्स के अबाउट डिस्कस कर लेंगे।
ठीक है। ओके ओके 5 मिनट की ब्रेक ले लें, ठीक है। डिस्कस करते हैं कोर्स। We have a break
थैंक
for
यू।
5 minutes. जी हेलो। हेलो।
अस्सलाम वालेकुम।
Yes,
जी
sir.
वालेकुम अस्सलाम। So from example 2.15 to onward, so I already have shared this document with you. Even you can consider it some example 2.14 as well. Example 2.13. Okay. So from example 2.10 to onward, you need to work out each and every example. So this is your assignment number 1.
सर एंड कहाँ पे होगी?
एंड होगी एग्जांपल 2.23.
Okay, sir. Thank you.
ओके सर।
So assignment number 1. So due by how much time do you need? I think it is very small assignment. You can do in 1 day or 2 days. So,
सर करना क्या है? थोड़ा समझ नहीं आया।
so due by April 26,
Yes, sir.
11 p.m.
No, Saturday.
Sorry, say again. So upload on LMS. So I will create a folder with this name assignment.
Okay, sir. Sir, मिड कब से लें?
So यहाँ पे फरवा पूछ रही थी करना क्या है, ठीक है? So फरवा,
यस सर।
you have studied complex number. So let A be the space of analytic functions defined on the unit disk D. So A is a set of space of analytic functions. So you can define in the unit disk D. So first you need to prove that it is vector space, the space of analytic functions. So in the unit disk D, and then this is a formula for the norm of any vector in this space. You need to show that this space of analytic function with this norm is a norm space, norm vector space. ये आपने करना
ओके
है, ठीक है?
ओके
तो
सर जी
यहाँ पे नहीं मतलब डिटेल given, so you need to work it out. So example 2.23 or example, for example, in that course in complex analysis you studied sum of two analytic functions is analytic. So if you multiply analytic function by a scalar, it is analytic function, right? So you need to justify that this space is a vector space with these two operations, vector additions and scalar multiplication. And then you will prove that the norm given by this formula satisfies those four properties. That norm of any vector is greater or equal to 0, norm equal to 0 if and only if the vector is equal to 0. ठीक है, this is assignment number 1, should be submitted by April 26th. So in the folder on LMS in your course. So example, so let me repeat example 2.10 to 2.23. So prove that the spaces are normed vector space. So first you need to prove that the given spaces are vector spaces. Then the norm defined on those vector spaces satisfies the properties of norms as well.
Sir, can you tell us about the midterm exam of functionals?
Midterm exam.
Because Dr. Azizur Rahman is going to take a midterm exam on 27th of the April. And what's about you?
Okay, so tell me, when should we do the midterm exam? When can we do? So can we do the midterm exam on Monday, May 3?
Yes, sir. It would be easy for us because on 27th we have already an exam.
So do you know the week number?
Sir, please discuss the syllabus.
So is it the week number 8?
यस सर, ये 8वां वीक है.
8वां, 9th week, 10th. So when can we do the midterm exam if it is not on May 3? So can we do on May 10th?
Yes, sir.
Okay, sir.
So I think May 10 is fine.
सर फिर हमारा सिलेबस कितना होगा 10 मई को?
जितना कुछ पढ़ा होगा आप May 3 तक.
सर आपने हमें फर्स्ट क्लास में कहा था कि मैं आप लोगों को एक प्रोजेक्ट दूंगा उसे एक्सप्लोर करने के लिए, तो सर आप वो भी हमें टाइम पे दे दें ताकि हम उसे एक्सप्लोर कर सकें.
ठीक है. So midterm exam.
यस सर, हमारी अभी तक कोई भी असेसमेंट नहीं हुई. एक हुई है बस, क्विज 1.
क्विज 1 और असाइनमेंट 1 आज मिल गया आपको, ठीक है। और क्विज 2 will be on, so that is due on 26 May. Quiz 2 will be, so can you do the quiz on Sunday?
Yes, sir.
I will upload the quiz, so I will give you maybe 3 to 4 hours so you can upload the solution. So can we do it on Sunday?
सर आप मेल कर
Sure,
दीजिएगा।
sir. Sure, sir.
Yes, sir.
So quiz 2 will be on, let me,
सर क्विज 2 का सिलेबस बता दें।
quiz 2 25 Okay, quiz 2 will be on Sunday, May 2. Right? So quiz 2 syllabus will be chapter 1, chapter 2. So the content we will discuss by 26 April, Monday. So next week तक जितना भी हमने पढ़ा होगा, that will be the syllabus for quiz Monday.
सर 10 मई को छुट्टी आ रही है।
10 मई को किस चीज की छुट्टी?
सर ईद की छुट्टी आ रही है।
ईद 10 मई को ही ईद है।
सर 10 से पहले ले लें।
सर 10 से पहले ले लें।
सर 3 मई बेस्ट है।
सर
Yes, sir.
8 और 9 मई को में से
सर
कोई एक
प्लीज 10
डिसाइड
से
करना।
पहले ले लें।
यस सर 3 मई बेस्ट है।
3 मई, okay, let me check. 10 मई को छुट्टी कैसे हो सकती है?
सर वो पूरा वीक छुट्टी दी हुई है इंस्टीट्यूट ने, मंडे से लेकर सैटरडे तक,
Oh,
जिसके अंदर ईद भी है।
let's see. So 10 मई को छुट्टी है तो
सर आप 8 को ले लें।
हाँ, किसी और दिन भी तो ले सकते हैं।
सर
8
फर्स्ट
को आप
वीक
ले
में
लीजिए,
घर भी
सेकंड
जाना है। सर फर्स्ट में को भी तो ले सकते हैं छुट्टी है। सर मैं एक के फर्स्ट वीक में लेने हैं, बाद में मैं घर जाना है।
अच्छा, ठीक है। सो May 3 को होगा मिड टर्म।
यस सर।
ओके सर।
सर ओके सर।
ओके सर, थैंक यू।
ओके सर।
ओके, So So this is section 2.4, finite dimensional norm spaces and subspaces. So 2.4.1 lemma is linear combination lemma. It's a very important lemma. This lemma is used in many results on finite dimensional norm spaces. So what does it say? X1, X2 up to Xn be a linearly independent set of vectors in a norm space X. So it can norm space X of any dimension. X1 up to Xn is a finite set of linearly independent vectors. So in a norm space X with any dimension, then there is a number C, positive number C, such that for every choice of scalars alpha 1, alpha 2 up to alpha n, we have the norm of the linear combination of alpha 1 x1 plus up to so on plus x alpha n xn. The norm is greater or equal to C time the sum of the absolute values of alpha 1, alpha 2 up to alpha n. So linear combination lemma. So for every choice of scalar, that means for every linear combination of the vector x1, x2 up to xn. So we have the inequality 1. Hold true for some positive real number C. So the next result, so maybe I can discuss, I will discuss the proof of this lemma in the next class. So in the next session, we can discuss the proof of this linear combination lemma. And one result in the next section 2.5, Rees lemma, and couple of related results. So in the next class, I will discuss the proof of this lemma, linear combination lemma, and the Rees lemma with some couple of more results before we start the linear operator. So then there will be 1 or 2 lectures on linear operators before we move to the next. So this lemma has many applications, linear combination lemma. So every finite dimensional subspace Y of a norm space is complete. So using this lemma, we can prove that every finite dimensional subspace Y of a norm space X is complete. So that means every finite dimensional norm space is complete. In particular, if you put Y equal to X, you get every finite dimensional norm space is complete. So you need to read this proof. So I will not discuss this proof of theorem 2.4.2. So you need to prove that finite dimensional subspace Y is complete. So you will consider an arbitrary Cauchy sequence in Y, and you will prove that it converges in Y. So using this lemma, you can prove it. So this lemma actually provides the opportunity to, so finite dimensional norm spaces are very similar to what you have finite dimensional Euclidean space. So alpha 1, alpha 2, alpha n are scalars. So you can use the Euclidean space, the results in Euclidean space to prove these results. So in each result, you will apply this lemma. So every finite dimensional norm space is complete. You can prove it using this lemma. Just read it. It's your reading assignment. 2.4.2. 2.4.3, every finite dimensional subspace Y of a norm space is closed. Remember, in metric space, we have, if metric space is complete, then a subspace is complete if and only if it is closed. So using that and the previous result, you can show that every finite dimensional subspace Y of a norm space is closed. So it is a corollary of the above result. And that result in metric spaces about the completeness of the subspace. Then 2.4.4, so is about the equivalent norms. So we have two norms on our non-empty set X. Let me show. Let me write. So if we have a non-empty set X, so let X be non-empty. Let X be a vector space. With norms one and two. The norms 1 and 2 norm are equivalent if there are scalars alpha beta such that alpha is greater than 0, beta is greater than 0. These are positive scalars satisfying this alpha time 1 norm less than 2 norms lesser equal to beta time 1 norm for all x in x. So then we say that these two norms are equivalent if there exists scalars alpha, positive scalars alpha beta. So using the linear combination lemma, we can prove that. So very important result. So on a finite dimensional vector spaces, any two norms are equivalent. Any two norms are equivalent on a finite dimensional vector spaces. So if you look at question number 3 and 4, 3 show that definition 2.4.4, that is the definition of equivalent norms we just discussed. The axioms of equivalence relations hold. तो equivalence
सर आपकी
relation
आवाज बहुत स्लो आती है, बहुत गौर से सुनना पड़ता है।
एक मिनट। क्या आ रही आवाज?
जी सर अभी से।
So equivalence relation is a relation that is transitive, symmetric and reflexive. So you can consider the relation on the norms on a vector space. So you have a set of norms and you define the relation. One norm is equivalent to another one. So every norm is equivalent to itself. So if norm 1 is equivalent to norm 2, norm 2 is equivalent to norm 1. If norm 1 is equivalent to norm 2, norm 2 is equivalent to norm 3, then norm 1 is equivalent to norm 3. So using the definition of equivalent norm, you can prove easily that this relation is an equivalence relation. So question number 4, maybe I will solve this question for. Show that the equivalent norms on a vector space X induce the same topology for X. So you have a norm space, you have the norm space X norm with respect to norm 1, X with respect to norm 2. So topology is same. That means if a set is open in one topology, it is open in the other one, if and only. So they both induce the same topology. They both generate the same topology, both norm spaces, if they are equivalent. So many other properties are being shared by the equivalent norms. For example, if two norms are equivalent, then the Cauchy sequence are the same. If one sequence is Cauchy in one norm with respect to one norm, it is Cauchy with respect to the other. So if a sequence is convergent in one norm, it is convergent in the other one. So many other properties are same for the equivalent norms. So in this, so try to solve the problems in this section as many as you can. So I will discuss, I will try to have a session, couple of sessions before the midterm exam about problem solving. Because in the exam there will be problems. The proofs, the theorems which we will discuss in the class. So I will not give those proofs. I will not give those statements to prove in the exam, which we did in the class or which we are already proved in the book. So the midterm exam will consist of problems. So like problems like the problems in these sections, examples, and the problems in the assignment. So maybe I will try to upload a document. So जितना भी 2.5 सेक्शन की कुछ चीजें हम अभी पढ़ेंगे 2.4 और 5 की नेक्स्ट क्लास में भी, तो कुछ प्रॉब्लम्स मैं आपको लिखूंगा प्रैक्टिस के लिए, जो मिड टर्म एग्जाम के लिए यू कैन प्रैक्टिस. So the problems I will mention with respect to each and every section. So question number 1, 2, 3, 4. So you can consider those problems for the practice for your midterm exam. That will be uploaded on LMS, or maybe I will try to send you via email as well. So, okay, that is all for today's lecture. If you have any question, you can ask any question, comment.
सर टॉपिक्स क्या ऐड कर दीजिएगा उनमें
टॉपिक्स किस में ऐड करूं?
जो हमारे मिड टर्म के टॉपिक्स होंगे ना वो भी
टॉपिक्स so when I will write the problems, like, so I will mention the section 1, section 2, or section 1.1, 1.2, 1.3. So those sections are included. जितनी भी चीजें उसमें हमने डिस्कस की होंगी ना, वो आप कंसीडर कर सकते हैं सेक्शंस.
ओके सर. सर हमारे सेकंड क्विज का सिलेबस क्या है?
सेकंड क्विज का सिलेबस है मतलब वेक्टर स्पेसेस और नॉर्म स्पेसेस.
And say what would be the time of the quiz?
Time of the quiz will be, okay, let me check what time of the quiz. Sunday, May 2. So quiz will be available from 10 a.m. to 2:30 p.m. on Sunday.
Okay, sir.
So I will upload these slides. So I will write the questions in this document. So
And say midterm exam timing will be same as the lecture timing?
yes. So questions for practice, I will write in this document in some time, and I will upload these slides, right? So you can find the questions for practice here.
Okay sir, thank you.
Okay. So if there is no question comment, I will end this meeting. Thank you so much. I'll see you next time. Allah Hafiz.
Sir attendance.
Allah Hafiz.
Allah Hafiz.
Attendance.
Sir attendance. Yes sir.
Attendance लगा सकता, next class से पहले आपकी attendance लगा दूंगा बाकी.
Okay sir.
Okay. Allah Hafiz.
Allah